Just a brief overview of what's in the slides. It's a short introduction on the Dutch geothermal potential. I'll pass on by a geothermal installation, then on to well design, well integrity, and then end up with strategic choices, considerations, and recommendations based on my time within the geothermal sector. So, one company which is important in the entire field of geothermal energy within the Netherlands, that's EBN, which is 100% state-owned Dutch vehicle. And for many years, they looked after safeguarding the profits from oil and gas for the Dutch community. Nowadays, they focus on 3 core areas: the gas transition, heat transition, as well as CO2 storage and transport systems. And the goal of EBN is to become climate neutral by 2050. What they do is every year they bring out some graphics on the energy which flows through a country like Holland. And to give you some idea on how much still is based around fossil fuels, there's this short presentation. So there is 83% of any kind of energy needed in Holland is made by 83% of fossil fuels. And the goal is to get away from gas altogether. And you have to bear in mind that 60% of the gas consumption is needed to produce heat. So if you want to go away from fossil fuels altogether, this gives you an idea of the massive undertaking of the energy transition, which is up for every country. So it's great to have such a state vehicle, and you can go online, have a look at the slides yourselves. And in 2018, I was working with Dago, and along with some other companies as well as EBN, we put together a master plan geothermal energy in the Netherlands. And the master plan for sustainable heat looked into how can you give shape to the 60% replacement of heat sources in the Netherlands. It's online. You can have a look at it. It's a very thorough piece of work. And in the end, the 60% of gas is being replaced by 25% solar, 25% wind energy, 25% geothermal, and still 25% made up from gas. So now stepping a bit into the Dutch subsurface. So the first 500 meters in Holland are free. Anything below 500 meters, then you have to deal with the Dutch mining law. And that's really a strictly regulated kind of exercise, because even though you drill for hot water, you still have to work along as if you're making a well which can hold, say, 500 bars. So, depending on the depth, you can see what you can supply heat to, and normally the hottest geothermal plant in Holland is 100 degrees. So that's not enough to produce any electricity from it, but in a way, it's the beauty because heat for heat has the highest revenues. There is hardly any loss in heat. So in the end, a prediction for 2050 was we then need to have 700 doublets. So that is 1,400 wells to be drilled, which is a massive number. And if you would have money to spend, I would buy a drilling rig. And of course, there is a lot of job creation involved in it. So just a slight question you don't have to answer. I will give you the answer, but how many wells in Holland are drilled deeper than 1,000 meters? Which are 4,000 of them. It's a massive number. And if you drill for oil and gas, or for geothermal, or for salt, you always have the same kind of contractors because it's highly regulated. As of today, there are 34 geothermal doublets in Holland, and there are 3 geothermal triplets. And a triplet is most of the times 1 producer well and 2 injector wells. Based on the previous slide, we are looking for yimbys. Yes, in my backyard. We don't need NIMBYs, we need yimbys. So, in the past, there were quite some seismic lines shot to identify the geology and look for oil and gas pockets, but it ended up in having quite some white spots in Holland. So especially in this part, there were hardly any lines shot, and EBN took up the opportunity to design and perform a scan program to shoot more seismic lines to better identify the geology underneath the white spots. And not only they shot seismic lines, they also performed a scan drilling program, and they drilled 8 vertical wells. All the data of the seismic lines, as well as the data, are being processed, and they are public. Just a short step towards permitting. As of 2023, there is an amended mining law, which is specially written for the geothermal sector. It's a lengthy period of time, So there are some stages. First, you have to apply for an area in which you try to find the best spot for your geothermal plant. Then you do your research. And if you've done your research and you think you're ready to start drilling, then get another permit. That's your startvergunning. And within this startvergunning, which runs for about 2, ultimately 3 years, you have to drill your well. You spend all the money in those 3 years. So if you would start this permitting time, it takes you about 5 years, maybe even 7 years before you can apply for the next stage, which is then a follow-up permit in which you are allowed then to produce geothermal heat for 30 years. So a quick look on a typical geothermal plant in Holland. This is a facility at Andijk. There are 2 doublets. The red ones, those are the producers, and each producer injects in a different injector. The wells are approximately 2,000 meters deep, true vertical. The temperature is about 84 degrees Celsius. The injection temperature is about 32 degrees, and the injection pressure is 50 bars at surface. The flow rate is about 330 cubes an hour, and it has 45 megawatt thermal capacity. Along with the brine comes 0.6 methane, which is then degassed at surface, dried and fed into a CHP unit. And apart from the geothermal drilling campaign and surface location, you also have to build up your heat network to connect all the greenhouses, which are in blue. Initially, these wells were made with a single skin well design, but they are now retrofitted with jerry-lined interchangeable tieback. And that's because of the high salinity of the brine, which eats away your LAD casing if you're not too careful. Here's a small picture of the surface installation. Here are the producers and injectors too, and they are completely separate from each other, and they can work independent of each other. This is then the well design. It's a bit complicated to dive into it right now, tell you all the nitty-gritty of it, but this is a special one because the production line with the ESP sits into a PBR, and when you have to change your ESP, pull your ESP, then the bottom part remains in the well, but you'll have full control over the annular pressures. A quick step onto the sources. This shows how much heat is required by the customers, which are greenhouses. So they still use a lot of combined heat power units burned with gas. And in 2021, there was only 19% geothermal, 8% biomass. There was 6% from a boiler in burning the gas which came with the brine. And there is a high temperature storage facility at a nearby location. In 2023, ECW was able to supply the greenhouses with about 60% of sustainable heat. And that's partly due to the high temperature storage facility, which has 18 megawatt thermal. And the idea behind it is to run your geothermal plant as much as possible. So in wintertime, you can only, so to say, produce the 64 megawatts, but you can then top up your megawatts with the megawatts stored in your high temperature storage, which you do over the summer months. So you will have a better runtime of your geothermal plant, because the beauty of geothermal is that you can produce the same heat 24/7 year long for about 30 years if properly designed. So just stepping into well design, well integrity. This is a picture of the initial well designs, single skin designs, with some explanation how each element is called. What's essential is to understand that there are always certain layers which seal. So it's not that the geothermal reservoir is into connection with your groundwater or whatever, and you're specifically looking to a caprock which is thick enough to hold the pressure differences you create by producing, and a thick enough reservoir to have enough volume of hot water to produce. So this is then for the well engineers under us, 13 3/8, 9 5/8, 6 5/8, and then the production string is then 8 5/8. In such an L80 well design, corrosion inhibition is essential because the choice was carbon casing. And because of the high salinity, it was shown in production time that loss of well integrity was quite possible. So initially, operators started to inject a corrosion inhibitor through a very small line, essentially injecting a soap, and soap doesn't want to stay in water. And ideally speaking, they would put up a double layer of atoms, of molecules, beside the steel casing, thus protecting the steel from corrosion. Unfortunately, over time, it was learned that that wasn't the case. So we're looking at alternatives to carbon steel, but then you have some material costs to take into account. So you can plastic coat L80 casing, which is then 2 times dearer. You can GRE line carbon casing, it's 2.5 times dearer. You can use full GRE casing, also 3 times dearer, larger diameter, so drilling costs go up. There is an alternative for composite casing. There is 13% chrome casing, which is 3 times dearer, and then you can even go up in chrome, but then you're unable to have a solid project because of all the costs and your low heat price. As opposed to this 3-stage well design, you can also drill in 2 or 4 sections. Try to save money by doing it in 2 sections, or be careful in drilling, going for 4 sections, but that's all depending on subsurface conditions and depth you drill to. And then I'll come back later on onto well designs into greater detail. So, based on the experiences of the first 10 years of geothermal in Holland, we realized that we needed to improve the well design, and that led to the industry standard for sustainable geothermal well design, of which I was able to have some input into it as well. So the key things are barrier redundancy, barrier independency, that you could monitor your barriers, and that your barriers are compatible with the environment. As a help, we did look at other standards, NORSOC, API standards. We even had a geothermal standard, which we looked at. And all these were incorporated into this sustainable industry standard. Here are some, how would I say, well designs which are fit under the industry standard. It has a shell which says a double barrier concept for the first section, which is like here. Within the mining law, it's stated you should have over the first 500 meters a double barrier concept, but you can also choose to go double barrier down to your reservoir section to have full control, either in 3 stages, 4 stages. You can stake with L80 casings, GRE lined, coated, or a completely different setup. In 2 sections, drill the well down into the reservoir, cement it in place, and then perforate afterwards. But we had an experience that over time you will be faced with sand ingress, so you'll have to install a screen inside your casing later on. Just a quick run through how is a well drilled. You first hammer a conductor in place, on average about 100 meters. Then you drill the next section, you case it. Then you drill the follow-up section, case it. Then you drill into your reservoir and put your sand screens into it. Then you best perform a production test with an ESP, and then later on install your GRE or coated inner string, or even a 13 chrome inner string, and then install the completion at the end, which is your producer with ESP. So, some economics again. This is a early single skin well design, which adds up to about 2.5 million euros of casing material. But then you would need corrosion inhibition, which sets you back about 80 to 100 euros a year. And in a single skin well design, you'll have to do a logging campaign at least every 5 years to prove to the state supervision of the mines that your well integrity is still there, and that you have to make a prediction how long your well integrity will last. Well, such a logging campaign will set you back about 400K. So your OPEX costs add up to 5.4 million over 30 years lifetime. So if you then go for a double skin geothermal well design with an interchangeable inner string, then you have to pay about 4.5 million. But then you don't have to use any corrosion inhibition. You're set free of logging campaigns because you can prove your well integrity 24/7 by pressure testing and annular pressure monitoring. Such a well design looks like this. I can go through to the details, but that's, I think, hardly the case. So to give you an idea, this is a double vault configuration. And if you would look closely, this is a G-lined inner string, which looks like this. Or you can choose for a coated casing, which looks like this. Here's just a simple 4-stage model, just to show that you can really design to whatever need you have in your project. Here are some alternative materials. This is a composite. There's no metal in the casings whatsoever. And it's coupled with steel couplers with the same OD almost as steel couplers. The strength in burst is okay, yet you have to worry about the collapse pressure. Another item is full GRE, which is made out of glass fibers, which run through a bath of epoxy, which is then put onto a rotating casing. And in the end, you end up with a full GRE casing. And in order to reduce the coupling OD, they now have a carbon fiber fit around a GRE coupling. Because of the time, I'll skip this one. Some strategic choices and recommendations. And before that, quickly, I'll go into what happens inside your well. So in this stage, you'll see the ESP is not running. And based on the weight of the brine, there is a static water level of 50 meters. But as soon as you would start your ESP, then the water level inside your annular drops down to say 590 meters, and your production casing is filled with water. So on the right-hand side, you'll see the top bit of an ESP, which has several elements. And the number of elements is crucial to produce your flow rate. So the factors influencing the pressure differences are the following: flow rate, formation pressure, temperature, specific gravity, which you cannot change, they are a given. The static water level depends on the specific gravity, the formation pressure, and the dynamic water level is based around the fluctuations in your flow rate, because your ESP can be tuned to your heat takeoff. And you have to be careful of certain horror scenarios that all of a sudden there's a power break and your ESP running on high voltage drops to zero. Then there is a water hammer in your injector. So there are no self-producing wells in Holland. Hence, you will always have to have a ESP in your well. And to achieve a high enough flow rate, such an engine may go up to 1500 horsepower. So to give you some idea, that's 15 car engines at 600 meters, 800 meters of depth in a corrosive brine. So imagine the precautions you have in such an ESP. And such an assembly may be as long as 35 meters, depending on the stages. So now, on pressure differences, it's getting a bit difficult. Hopefully, I will not fry your brains in it, but I'll try to explain why you have to look at pressure differences. So again, you don't run your ESP. So the static water level is, say, 25 meters below surface. Your SG is 1.12. You have about 90 degrees Celsius of heat you can produce. And because you produce on a high flow rate, there is some friction factor to take into account. So, static water level, that means on 800 meters, you'll have a pressure of, say, 87 bars. As soon as you start up your ESP, your static water level drops down to a dynamic water level, ultimately safeguarding 300 meters above the inlet. So then you'll have 34 bars on the outside of the casing. On the inlet, within your ESP, you'll have about 111 bars, because you want to have 10 bars at surface, which is because of degassing the brine. You don't want to degas the brine when inside your producer. So then you can check the pressure differences. So say your dynamic water level is about 500 meters. Then here inside your well you have 0 bar, in your annular, you'll have 95 bars, 59 bars, sorry. And then at your intake, you'll have 93 bars in your annular space. But again, based on the 34 bars at the height of this 300 meters. So the pressure difference, more or less quickly said, is 59 bars all the way down. If you would lower your ESP to about 1200 meters, then the numbers change a bit. So your dynamic water level remains 300 meters above your inlet. So you'll have another 34 bars, but because there is a higher water volume in your annular space based on the specific gravity, you'll have 138 bars. So instead of the 59 bars, you'll have to face 104 bars all the way down. So why is that of importance? Because you also have to look at your injector well, in which you have about 60 bars pressure to get your flow rate covered and put your cubes, say 300 cubes an hour, back into the reservoir. So your injector is fully filled, completely filled, down to the wellhead, and you'll be faced with different pressures in your annular, which then have some relation to your formation strength and the pressure coming from the formations you drilled to. But in the end, you could state, well, why would you need a premium connection in your casing when you're only faced with 62 bars or 100 bars? So you could also do with semi-premium. But then again, as mentioned earlier, when your ESP shuts down in an instant, you'll be faced with water hammering and your pressure differences go way out of scale. So you have to be careful in choosing the right connection. So just to summarize, I think I'm good for timing. You'll have to carefully choose a well design, and I would strongly recommend a tieback string, which can be pulled at all times, because the one certainty in any technology is it will break. And it may take a while, but it will break. On surface, you can replace any unit. In subsurface, the casings stay where they are. And if your well integrity is lost, you have to install another casing string with a smaller diameter in your well, which then reduces your ability to produce heat. Another thing is, in choosing your well design, there are a lot of hidden costs which are in your OPEX. So if you're going for a low CAPEX as possible, you might end up going bankrupt on your OPEX costs. As well as drilling too large a well will set you back with extra cost, because drilling a drilling operation fully functional sets you back about 75,000 to 80,000 euros a day. So you can save some money in choosing a slimmest well design possible, yet trying to achieve a largest possible inner diameter of your tieback string, because the more flow you can generate, the better you can produce. Consider if semi-premium connections can be used instead of premium. Consider well where flush threads can save your inner diameter string diameter, and especially operating an ESP is an art, because if you're too rough with your ESP in producing, changing settings too quickly, your ESP will fail drastically, and you'll have to pull your ESP, which will then set you back 200, 300, 400K. So in the end, the longer you can let your ESP run, the better it is, and the better it is for your bank account. And with this, I'd like to conclude my webinar.